Okay, so now we've looked at polynomials and we've looked at how to solve the polynomials by finding the zeros. We've looked at rational functions, we've looked at all the tricks to graphing rational functions. Now we actually want to kind of go back to where we started, because going all the way back to the first chapter, the way this works is, generally speaking, you start with something like an equation. And then once you can solve that, all of you can solve that, not a big deal. Then you say, if I can solve an equation, then maybe I want to solve an inequality and see what happens then. And if we recall how we solved these at the beginning of the semester, to solve the inequality, you essentially treat it like an equation, do everything you would normally do with the equation, and then get an answer at the end. The only difference is, instead of getting maybe one answer, you get a whole interval as a solution. For this one, instead of getting x equals 1, you get x is less than or equal to 1. Now, since we've looked at polynomials and rational functions, we want to do the exact same thing. And we want to look at things like x squared minus 6 is less than or equal to 0. Polynomial, or in this case, quadratic inequalities. And as far as it goes, we can use the same setup that we did before. In order to solve this, first, pretend it's an inequality. Now, if it was an equation, I would just say, okay, factor it. X minus 3, x plus 2. Then you would find the zeros, x equals 3 and x equals negative 2. So we can kind of do the exact same thing here. Set it to 0, which it already is, factor it, find the zeros. But now, using what we know about quadratics, I know if I have a 0 at 3 and a 0 at negative 2, the leading coefficient is positive, so it opens up. So the graph is going to look something like that. But before I just cared about the zeros, I found them and I was good. Now I care about where it's less than or equal to 0. But if we look, these zeros essentially break this up into 3 regions. All the x's over here will give me a positive function value. All the x's inside here will give me a negative function value. And all the x's out here will give me a positive function value. So the solutions would be everything in between here. I guess in this case, the interval from negative 2 to 3. Because that's all the places where the function is less than or equal to 0. But since I don't necessarily want to have to graph these things out each time, it would be beneficial if I could see a trick. And the idea is, I know this is what all polynomials will look like, and quadratics, cubics, you name it, where if I break up the real number around the zeros, like I did here, in each region around those zeros, the graph is either always positive or always negative. So then, I can create what's called a sign chart. And the idea is, I find my zeros and label them. I had 1 at 3, I had 1 at negative 2. Now, since I know if one value in between negative 2 and 3, say 0, if I plug that in, 0 minus 6, I get negative 6. So at 0, the graph is at negative 6. Then logically, the graph has to look like this. And every point between negative 2 and 3 has to give me a negative value. So I just put the sign right up here, negative. That's why it's called a sign chart. So all I'm going to do now is pick a point in each region, plug it into the inequality, and see if I get positive or negative. If I plug in, say, 4, because that's over in this region. 4 squared is 16, 16 minus 4 is 12, 12 minus 6 is 6. That's positive. So everything in this region will be positive. Pick something to the left of negative 2. Go with negative 3. Negative 3 squared is 9. 9 minus negative 3 is 9 plus 3, which is 12. 12 minus 6 is 6. That's positive. Now I have the sign of each region. So now I just answer the question. I want all the places where this is less than or equal to 0. That's all the places where it's negative, which is right there. Which is, of course, exactly what we just got when we looked at the graph. But now, rather than creating a graph, I can just create this quick little sign chart. Find the zeros, pick a point in each region, plug it into the inequality, see if you get positive or negative, and then pick the regions you want. So, to do this one more time to get the idea, suppose I have x squared plus 13x plus 30 is greater than or equal to 0. And actually, I'm going to change this to just greater than. So what do? First thing, pretend it's an equality, so factor it. Two numbers multiply to 30 that add to 13, that would be 10 and 3. So x plus 10, x plus 3 is greater than 0. I would also point out, it goes without saying, I'm setting both of these to 0. If you had an inequality that was not set to 0, just like when you're solving quadratics, the first thing you do is set them to 0 so that these tricks will work. Now that I have this, I get my solutions. X is negative 10, x is negative 3. Then I draw a sign chart. There's negative 10, there's negative 3. I pick a point in each region. To the left of negative 10, I get negative 11. Let's see. Negative 11 squared is 121. 13 times negative 11 is negative 143 plus 30. 121 plus 30 is 151. 151 minus 143 is 8, which is positive. Between negative 10 and negative 3, I'm going to go with negative 4 because it's smaller. Negative 4 squared is 16. 13 times negative 4 is negative 52 plus 30. 16 plus 30 is 46. 46 minus 52 is negative. Pick a point bigger than negative 3, go with 0. 0 plus 30 is 30, which is positive. Now, I want where this is greater than 0, that's where it's positive. So now I get two intervals, not one. The one thing to be aware of, though, negative 10 and negative 3 are zeros. In this case, I only want where it's greater than 0, not greater than or equal to 0. So now I don't want to include those points, the end points. So I do negative infinity to negative 10 open, union, negative 3 open, to positive infinity. We've already done the closed open thing earlier in the semester, so that's pretty straightforward. But just remember that. If this was greater than or equal to, my answer would be the same, but those would be closed right there. There's one other type of inequality we want to look at. Rational inequalities. So suppose we have x plus 2 over x minus 3 is greater than 0. In this case, this is a rational inequality. The first thing you do is set it equal to 0, just like we did before. And now I'm going to use my sign chart like I did before, but there's another trick I'm going to add here. In this case, we know how rational functions look. I need to find the zeros, so I know where it's positive and negative. This has a 0 at negative 2. But now if we think about the asymptotes on a rational function, I also have to find where that rational function is undefined. In this case, it's undefined at positive 3. So now, once you have a rational function, you break up your line around the zeros and the places where it's undefined. Now, do the exact same thing. Pick a number less than negative 2. If I plug in negative 3 plus 2 is negative 1. Negative 3 minus 3 is negative 6. Two negatives cancel and you get positive. If you pick a number between negative 2 and 3, go with 0. 0 plus 2 is 2. 0 minus 3 is negative 3. Positive over negative is negative. Oh, I will say now that we've done several of these, I don't really care about the value here. That's why I'm not really going through in any great length what they are. All I care about is the sign. Negative, negative gives positive. Positive, negative gives negative. The value is kind of irrelevant. All you care about is its sign. Pick a number bigger than 3. Go with 4. 4 plus 2 is 6. 4 minus 3 is 1. That's positive. Now I want where it's greater than 0, so I want this region and this region. So I do my little intervals, negative infinity to negative 2, union 3 to infinity. We're going to do one more of these to do a little bit more algebra, but just be aware, all the ones we've done so far have been positive, negative, positive, or negative, positive, negative. That's not true in general. It's true for quadratics, it's not true in general, and it's not true for rational functions. So don't just find the first one and say, oh, I'm just going to keep switching the signs. That's positive, it's got to be negative, positive. Always check each interval. Okay, so lastly, suppose I have x plus 1 over x minus 3 is greater than 1. The difference here is, we're going to go with greater than or equal to 1. The difference here is, this is not set to 0, so set it to 0. Subtract the 1. You get x plus 1 over x minus 3 minus 1 is greater than or equal to 0. Now the problem is, well, this is not a rational function. It's a rational function minus 1. In order for this trick to work, you have to write this as a rational function, which means I need to turn this into one big function. So I'm going to multiply the 1 by x minus 3 on top and bottom. Then this becomes x plus 1 minus x minus 3 all over x minus 3 is greater than or equal to 0. Which then simplifies x minus x is 0, 1 minus minus 3 is 1 plus 3, which is 4, over x minus 3 is greater than or equal to 0. That's all simple algebra you can do. But now, I have it written as a rational function, greater than or less than or equal to 0. Now I can apply my sign chart. There's no zeros on top because there's no x's, so I don't have to worry about that. There is a 0 on the bottom at x equals 3. So now I have a nice sign chart, pick a number on either side. If I pick a number to the left, go with 0. 0 minus 3 is negative 3. Positive over negative is negative. If I pick, say, 4 on the right, 4 minus 3 is 1. 4 over 1 is 4, which is positive. I want where it's greater than or equal to 0, so I want this side. So then my solution is the interval 3 to infinity. The one question is here at 3, and normally if it's greater than or equal to 0, I include that endpoint. But with rational functions, you have to be careful, because this endpoint is not where the function is 0. We said there is no zeros. This endpoint is where it's undefined, which means that's not where it's 0, so I don't include it. It's always open. So just be aware when you're doing these. If you're doing polynomials like we started with, if it's greater than or equal to or less than or equal to, you include the endpoints, close brackets. If it's just greater than or less than, parentheses, don't include the endpoints. If it's a rational function, you have to check each number individually. If there's zeros, see if you want to include the zeros or not. If they're where it's got an asymptote, where it's undefined, then you never include it. You have to always leave it as a parenthesis.